Welcome to the exercises for chapter 12. This chapter is all about correlations, correlation analysis, different kinds of correlation algorithms, and statistical significances of correlation coefficients. So the first exercise is pretty straightforward. It's just about implementing the formula to compute the Pearson correlation coefficient directly, just from the math of the equation, without using basically without using CoreCoef or Pearson R functions in NumPy or SciPy. So what you want to do is create two random variables and impose some kind of a correlation between them. Now, you learned in this chapter several methods for creating correlated variables. You can do it as sophisticated as you want. My solution is actually a pretty straightforward way of creating two random correlated variables, because the main point of this exercise is not so much about the correlation coefficient itself, but just to make sure that you understand the math of the Pearson correlation coefficient well enough that you can implement it and get the same result that you would get when using NumPy. Okay, so implement equation 12, I'll show you that in a moment, and then compute the correlation coefficient using NumPy to confirm that your implementation of the formula is correct. Okay, so let me show you this equation here. So here is equation 12, and this is the equation for the Pearson correlation coefficient, often labeled R. So you sum over all of the data points, and then you multiply each corresponding data point, so x times y, but then you have to mean center. So x minus the mean times y minus the mean, that's the numerator. And the denominator is looks pretty similar. All right, so this term is the same thing as this, except it's squared. And then this term is the same thing as this, but then it's squared inside the summation. And then you take the square root of that to give the denominator. Okay, so now I will switch to Python and show you my code solution. Here I am creating two random correlated variables, and the way that I impose the correlation is simply by defining w to be v plus some random number. So that is the simplest, easiest, straightforwardest way to create two correlated random variables without worrying about what the exact correlation coefficient is. Okay, here I mean center, and now I'm computing a slight variant of the equation that I just showed, and that is the dot product between v and w. I call these variables m for mean center, divided by the square root of the dot product between vm with itself and wm with itself. And then here I use NumPy to compute the correlation coefficient, and we should get the same answer. Now, it doesn't matter what this number is. What matters, so each time you run it, you're going to get a different result. What matters is that each time we run this code, these two lines or these two variables give us the same results. That tells us that we have correctly implemented the formula for a correlation coefficient. Needless to say, in practice, it's much easier to do this line of code than these three lines of code. But as I often do in the exercises for this book and also my other books and courses, I think it's really informative and really helpful to implement these functions and these algorithms yourself. And then once you have a good grasp of how it works, then of course, in practice, it's much easier just to call this one line. In the previous exercise, you implemented the formula for the Pearson correlation coefficient directly, and then confirmed that you got the right answer. And now in this exercise, exercise 2 of chapter 12, the goal is to make sure that you know how to compute a p-value from a correlation coefficient. So it turns out that numpy.corecoef returns the correlation coefficient, but not the associated p-value. So you don't get an associated p-value. However, I showed a formula, I showed an equation in this chapter, and I'll slide up to that in a moment, that you can use to compute a t-value from an r-value, and from the t-value, you can compute a p-value. So the first goal of this exercise is to get a correlation coefficient from numpy.corecoef, and then get its associated p-value by implementing equation 24. And again, I'll show you that in a moment. Okay, and then you can compare that to the output of the stats.pearsonr function, which is in the scipy.stats library. And well, the thing is that the Pearson R function returns both the correlation coefficient and also the p-value. So you can actually get a p-value here. So we want to see if Pearson R in the stats library gives the same p-value that you get when you implement equation 24. Okay, so to start with, create two variables that are drawn from a population that has a correlation of 0.1 and a sample size of 43. And I will show you that formula as well. Let's see. And then, okay, so then you basically compare your result with NumPy and computing your own p-value, that's this in here, with the output of SciPy and the p-value output from SciPy. So what you see is that the NumPy and the SciPy results are identical. They are the same. And the p-values are similar, but not identical. So that's funny. So, So then you can run this again, trying different values of R to see how often the correlation coefficients are the same and the p-values are the same or different. And are they a lot different or just a little bit different? So that is the first part of this exercise. And then the second part of this exercise is basically to go through this more methodically, more systematically. So what you want to do is keep repeating this experiment, but for a range of correlation coefficients. So basically, in a for loop that runs over all of these different correlation values, you compute the correlation or create two random variables that have this correlation value as their population correlation. And then compute the two p-values from NumPy, where you get the p-value yourself, and then from SciPy, which also outputs the p-value. And then basically just plot them as a function of the correlation coefficient. Here I plotted log p. I'm also going to show you the linear scaling of the p-value in the code. And well, I'll have a few interesting things to remark about this when I get to the code. But first I will show you the two formulas to use, and then we'll switch to code. For starters, here is equation 22. This is how you generate two random variables that have a specified population correlation of R. So you start off with X, and I call this here Y tilde, both standard, normal, distributed random numbers of whatever sample size you choose. And then you apply this formula here, and that gives you Y. And now Y and X are two random variables that are drawn from a population with a correlation coefficient of R, whatever you specify as this R value here. And then here is equation 24. So this is the formula to get to a t value from a correlation coefficient. So given an empirical correlation between two variables that are sampled, so this is not the population correlation value, but the sample correlation, and based on the sample size, then you apply this formula that gives you a t value with n minus 2 degrees of freedom. And then you can evaluate this t value with these degrees of freedom in a PDF for a t statistic to get the p-value. So that's how you get the p-value from the sample correlation coefficient, which you will then compare against the output of the Pearson R function from scipy.stats. Okay, so quite a few things to do in this exercise, but I hope you found this enjoyable to work through. So let's see, here's our two random variables, and this is just the direct implementation of the formula that I showed in the slides. Here you can see, or in the book text, sorry, here you can see the correlation coefficient using NumPy. And here I'm getting the t value according to equation 24, which I just showed. And then here I'm converting that into a p-value, and I'm multiplying it by 2 because we are doing a two-tailed t-test here. And then here's the output from the stats.pearsonr function. So now when I run this, you can see that the correlation coefficients are identical, at least up to 4 numbers after the decimal point. And the p-values are not identical, but they're super duper similar. Okay, so again, you see same fact. It's going to happen over and over again. So let's see. Now what I want to do is increase this to, let's say, zero point 0.4. And just to show you again that the correlation coefficients are identical. So that's a good thing. And the p-values are slightly different, but really close to each other. And that is puzzling. Okay, so now we get to the experiment. So here we have a for loop. Let's see. So the actual experiment actually starts down here. So I'm looping over these correlations. So 40 correlation values between 0 and 0.99. Generate the two data sets, and I get the two p-values using this function that I wrote here called get p-vals. And that is a function that takes in two variables, x and y. It computes the correlation coefficient from NumPy, the p-value, and then the p-value from the stats.pearson r. And I'm only outputting the p-value because for this exercise, we don't actually care about confirming, like how close the R value is to the specified value, the population correlation. We just care about the p-values. Okay, so we can run this code here, and then the rest of this code is just plotting. So what you see is that for small correlation coefficients close to 0, the two p-values are really, really similar. They almost look identical. This one you can see looks a tiny bit different, but the larger the p-value, the larger the correlation coefficient, the larger the difference between the two p-values. Now this looks really extreme, but in fact, if we don't plot this on a log scale, so now I'm just going to get rid of this log function here. And now you can see that these correlations look really, really close to each other because they're both very, very small. Here you do see some discrepancies and so on. Let me go back here. So basically, when you apply the log to very, very small values, very close to 0, it really stretches them out and makes tiny, tiny differences seem much bigger than they actually are. But the question is, why are there these differences and which one is correct? Well, the answer is that the answer to the second question is neither is incorrect. They're both correct. They're just slightly different formulas for computing the p-values. And basically, SciPy is applying a non-standard, but that doesn't mean it's bad, but applying a small correction factor to the p-values to account for the fact that the correlation coefficients are bound by -1 and +1. And so they're not normally distributed correlation coefficients. They have a uniform distribution, or at least uniform bounds. And so that is why the adjustment factor has a bigger impact when the correlation gets larger because you're getting closer to the bound. Now, does this matter in practice? I don't know. I think it would be exceptionally rare to find circumstances where using one method over the other method would lead you to a different conclusion about whether the two variables were correlated. So I wouldn't worry too much about this difference here. Here we are with exercise 3 of chapter 12. This exercise and the next exercise are focused on correlation matrices. So not just correlating one pair of variables, x and y, but instead correlating an entire data matrix, like a data frame that is based on taking lots of variables, so lots of different data features, organizing them into columns of a data matrix, and then you want the pairwise correlations across all possible pairs of variables. Okay, so this is a theme that will come up quite often. You'll see it again, in a later exercise. We're going to do something a little bit similar in Pandas. Here, we are only going to use NumPy. And basically, the idea is that we want to compute a random matrix. So let's see, you want a data matrix of observations by features with 10,000 observations and 15 features. If you want, you can impose various correlations across these variables, but you don't have to worry about that because we're really just worrying about the code implementation. So I actually just created these all to be random numbers with no correlations specifically imposed in the data. Okay, and then we want to compute the correlation across all possible pairs of variables. Now, the thing is that stats.pearson.r will return p-values, but it does not support matrix inputs. NumPy, on the other hand, supports matrix inputs, but does not return p-values. What an annoying feature of how Python that is. But anyway, okay, so the goal here is to create this data matrix of random numbers, use NumPy to create a correlation matrix, and then compute the p-values using the methods that I described earlier in this chapter and that we also covered in the previous exercise. In the end, you're going to get a figure. You're going to create a figure that looks something like this. So here is the correlation matrix across all pairs of data features. Here I call this channels, but it doesn't matter. And then you convert that into a T matrix. So these are all the T values for all the pairs of data features. And then this is the p-value matrix. So the element in each, the numerical value of each element in this matrix is the p-value between each of this t-value, which is the correlation between this data feature and this data feature. I hope that makes sense. I'm now going to switch to Python and walk you through my solution. So here is where I create the data matrix, which is just random numbers here. But you can see how I've organized it is observations by features. So although this is just pure random numbers, in practice, in real data, this is how you would most of the time want to organize your data matrix as observations by features. Here I create the correlation matrix, and now this is, maybe perhaps you find this a little confusing or a little annoying, but for various linear algebra implementational reasons, the core color function is actually expecting the features to be in the rows and the observations to be in the columns. So it's slightly backwards. If you're ever confused, it's totally fine. It's totally reasonable. Everyone gets confused about this stuff. The way to determine if you're doing the right thing is to look at the shape of this correlation matrix. And a correlation matrix should always be of size, features by features. So measurements by measurements, and not the observations by observation. So in this case, we see that this correlation matrix is 10,000 by 10,000. Well, 10,000 is the number of observations, so therefore it's wrong. So we know that we just have to transpose this matrix, and now we get a correlation matrix of 15 by 15. If you are familiar with linear algebra, especially if you've taken my online linear algebra course or read my linear algebra books, you will understand why you get this difference and why you need to transpose. If you're not familiar with linear algebra, then don't worry about it. It's not a big deal. The important thing to know is that it is very easy to correlate the wrong way. And it's also very easy to check to confirm that you're doing it right, which is just to look at the size of the correlation matrix. Again, it always needs to be features by features. Okay, so now we get our correlation matrix. Here I get the T statistic for each pair of correlation values. We can do this all vectorized. We don't need to do this in a for loop. Here I've just added epsilon, just machine epsilon, just a tiny, tiny, tiny number. And that's basically just to account for the possibility that if the correlation happens to be 1 or extremely super duper really a lot close to 1, then we're going to be dividing by 0, which is going to give us problems. So this just adds a tiny, tiny number to make sure that we're never really dividing by 0. Okay, and then I compute the p-values of these t-values. This is the same as what you've seen before. The only difference is now here it's a matrix instead of just one number. Okay, and then I'm using imshow to create these matrices, to visualize these matrices. Okay, so here you go. This is all random data, so we literally cannot interpret any results here. But you do see that there's ones on the diagonal that we expect. You can kind of see that this is a symmetric correlation or a symmetric matrix. So like this element equals this element equals this element, and so on. that we expect. Correlation matrices should be symmetric, and therefore also the T matrix and the p-values matrix will also be symmetric. Here we are with exercise 4 of chapter 12. Just one little note of warning about this, which I have here in italics. This exercise is entirely about linear algebra and matrices and converting between correlation matrices and covariance matrices. If you are not at all familiar with linear algebra, then that's totally fine. You can skip this exercise if you want, or you can decide not to work through the code on your own, but just to watch me talk about my solution. Any level of engagement that you want to have with this exercise is great. It's totally fine. If you're not familiar with linear algebra, that is not in any way going to prevent you from being able to successfully apply and interpret correlation analyses. Okay, so with that said, basically the goal is to translate between the covariance matrix and the correlation matrix using a sigma matrix, as discussed in section 12.3.1. So I'll show you this in a moment. And then you also want to use numpy.cov to get the covariance matrix and numpy.corecoef to get a correlation matrix to confirm that your linear algebra implementations are accurate. Okay, so now let me show you the formulas here, and then I'll switch to code. So here is section 12.3.1, which is all about the matrix implementation of correlation and covariance matrices. So start by creating some data matrix X. It should be n by m, corresponding to n observations and m data features. Okay, and then basically before getting into any of this linear algebra stuff, you need to do two normalizations. You need to d-mean, so mean center each column, so all the features are mean centered, and then scale by n minus 1, so the number of data points minus 1. So that's the first step. The next step is to compute the covariance matrix, which is very simple. Once you have applied these two normalization steps, you simply take x transpose times x, and that gives you matrix C, which is the covariance matrix. Okay, and then to transform that into R, you apply this formula here. So R equals sigma inverse times C times sigma inverse. So you left and right multiply by sigma inverse. So what is sigma inverse? This is a diagonal matrix, so it has all zeros on the off-diagonal elements, and the diagonal elements are the standard deviations of each data feature. Okay, and that is how you get R from C, and then basically you just turn this around, and you get C from R by pre and post multiplying by the sigma matrix. Again, this matrix is all zeros, except for the diagonal elements, which contain the standard deviation of the variables. Okay, so now I'm going to switch to Python and show you basically just the implementation of these formulas and the confirmation that these are correct. I am using here the same data matrix that I created in the previous exercise, exercise 3. So we take the standard deviation. This part is straightforward. You're very familiar with this. Just have to make sure that you are taking the standard deviation with a specified axis. Let me show you what happens if you do not do this. So I'll show you what happens when you do it, first of all. And here you see that we get a standard deviation, thinking a very long time about this standard deviation. So here you see that we get 15 numbers coming out corresponding to the standard deviations, the sample standard deviations of each of 15 features in this data set. Now they're all pretty close to 1, but that's not surprising because these are just randomly drawn numbers from a standard normal distribution. What I wanted to show you is that if you don't specify the axis, then you're going to get one number, and that is the standard deviation of all of the elements in the entire matrix. Of course, there might be cases where that is the desired output, that's what you want, but it's certainly not what you want here. Okay, so that's why we need this axis equals 0 here. Here I create the sigma matrix as a diagonal matrix generated from those 15 numbers that I just showed you. Okay, so then let's see, here I'm computing the covariance matrix from the correlation matrix using R, which I computed in the previous exercise using NumPy. So sigma R sigma. And then here I'm computing the covariance matrix using NumPy. And then basically I'm just saying here, what is the difference between these two matrices? And is this smaller than some tiny, 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 tiny number? And those are all trues. Okay, there's a couple of falses here. But yeah, I mean, these are just rounding errors. We can see if we make this tolerance a little bit bigger, okay, we still get a couple of rounding errors in here. But anyway, these are, okay, maybe we can just print out this difference matrix like this. You can see all these numbers are either 0 or they are, something like 10 to the minus 18, minus 19, minus 16. These are all tiny, tiny numbers. Okay, so then we turn this around, and now I'm going to compute the correlation matrix from the covariance matrix. So this is the covariance matrix from NumPy, and here I'm computing inverse of sigma. Now, if you are familiar with linear algebra, you will know that for a full matrix, the inverse is not equal to the reciprocal of each element individually. However, there is an exception for a diagonal matrix. If you have a full rank diagonal matrix, then to invert that matrix, you leave all the zeros on as they were. So you still have a diagonal matrix. And then the diagonal elements are literally just the reciprocal of the original diagonal elements. So this is a special exception in linear algebra to get the inverse in a computationally efficient and stable manner. Okay, and then again, we're comparing the correlation matrix that I got from NumPy in the previous exercise with this correlation matrix that's defined from or computed from the covariance matrix. And again, the difference matrix minus some little tolerance level is all true. So that tells us that these are the same values. Welcome to exercise 5 of chapter 12. This exercise goes in conjunction with the following exercise, so I recommend having a nice big chunk of time to do both of these exercises because the conclusion that you are going to draw from this exercise is going to be negated by the next exercise. So it's going to be a demonstration of how statistics can be pretty tricky to do, especially when it comes to averaging in different ways. So in fact, what you are going to do in this exercise is create a data set and start adding noise to it over different repetitions, and then basically compute correlations of each repetition and then average the correlation matrices, or you will average the data together and then you will compute one correlation matrix on the data average. So the question is, do you average data or do you average correlation matrices? Okay, so that is the high-level picture. Let me now explain in a little bit more detail what you should do in code. So what you want to do is create a data set that is contains 1,000 observations, 20 features, and 30 repetitions. So a repetition is like a repeat. Like you're doing an experiment, you repeat the same experimental environment, the same condition 30 times. So 1,000 observations, 20 data sets, 20 features, and 30 repetitions. Okay, so like 30 data sets. But these are not independent data sets. They're all similar to each other. And how are they similar to each other? They are similar to each other in that they all come from the same covariance structure. So create a covariance structure across the 20 different, was it 20? Yeah, 20 different data features as linearly spaced numbers between -1 and +1. So the idea here is that this is going to be a vector of numbers from -1 to +1, and that is your covariance structure that you will impose on random data. Now, if you are familiar with linear algebra, you will recognize this expression as the outer product between this vector containing random numbers and this structure which contains this vector which contains the covariance structure. So if you implement this code, this is going to give you a variable. I call it data OG for original gangsta. It's the original data gangsta. And that is random numbers, but these are correlated random numbers. They have a covariance structure. Okay, so then we can visualize that covariance structure. It looks like this. So this is actually just the outer product of that covars vector with itself. Okay, so this is the covariance structure. And then you generate random data, or you have the random data OG. And then over the course of these different repetitions, you basically take this data variable, this data matrix, and then you add some noise to it. So how much noise to add, I will leave that to you to experiment with. You will find that you get slightly different results when you add different amounts of noise. Yeah, that's something you can play around with. Okay, so again, just to make sure this is clear. So at each iteration inside a for loop over 30 different iterations or repetitions, you have this variable which you've created outside the for loop. So you create this before doing the for loop. And this data matrix is 20 features by 1,000 observations. And this is how you create that data matrix, the original data matrix. And then inside the for loop, you add random noise to this data set into a separate variable because you don't want the noise to accumulate. So the original data gets repetition unique noise. And then within this for loop, you want to do two things. You want to start accumulating the data so you can average it together over all 30 iterations. And then you want to compute the correlation matrix of that repetition unique data set. That is this thing plus noise. Now, that's not the accumulation for averaging. It's the correlation of the original data OG plus repetition unique noise. So at the end of this simulation, at the end of your iterate your for loop over 30 iterations, you're going to have 31 correlation matrices, 30 correlation matrices that correspond to the correlation matrix of each individual data repetition, and then one correlation matrix at the end, which is the correlation of the average of all of the 30 repetitions, the 30 unique repetitions. You average them all together and you compute 31 correlations. And then what you visualize here is the ground truth. This is the covariance structure, as I've explained. And then we can have two different ways of averaging together. So this is the average of the correlation matrices. So this is your average of the 30 correlation matrices, one correlation matrix for each repetition. Average those together. And here, what you see is the average of all of the data. And then you get one correlation matrix after averaging together all of the data. Okay, so then, I have a few remarks to make about this. Now I will switch to code and show you my implementation. This is admittedly a very tricky exercise to explain. I hope that I've written it clearly enough and explained it clearly enough. It's kind of weird, but it does mimic real applications. In my research lab, we have to make choices about whether to average and correlate using the method I describe here, exercise 5, or what you'll see in the next exercise, exercise 6. So anyway, here I have the variables soft-coded, so 1,000 observations, 20 features, 30 repetitions. Here is, this is just the code that I had in the book. And here is the for loop over the different repetitions. So the data for this repetition is data OG. So we're not creating new original data. Data OG within each iteration here, plus random noise. And now this multiplicative factor of 5 is just a scaling number that I found to work pretty well. Okay, so here we get the correlation matrix of this data. So this is not the correlation of OG. This is the correlation of data OG plus repetition unique noise. And then I'm storing all the data. So here I'm summing up all the data, which is the sum over all of the data OG plus this random noise here. And then here I compute the correlation matrix of all of these data averaged together. Now, technically, this is the sum, it's not the average. You can get the average by dividing by 30 or, in general, dividing by uh, num reps, this parameter k. But that's just a scaling factor. It literally does not change the correlation coefficient. As you know, correlation coefficient is independent of the scale of the data. Okay, so I hope it makes sense. Here's how we get our 31 correlation matrices. The correlation matrix of each repetition with unique noise, and then the correlation of all of the data without or summing over all of the noise. Okay, so then we visualize that. And now I think the conclusion from this experiment is pretty clear. This correlation matrix, so the correlation of the data average, is much, much closer to the ground truth compared to the average of the correlation matrices. Okay, so before you think that that is how you should always deal with correlations, that you should always average data first and then compute one correlation. And the wrong way to do every analysis is to average correlation matrices. Before you start thinking that, go to the next exercise, and I'm going to show you a very, very small change to the experimental setup that will completely change this conclusion. Here we are with exercise 6 of chapter 12. You need to have done exercise 5 before working through this exercise. In fact, this exercise is nearly identical to the previous one. You can copy all the code from exercise 5 into exercise 6, and you make exactly one change, one conceptual change. And that change is that the original data, so the pure data, what I call data OG in the previous exercise, that is created inside each repetition of the for loop instead of being created outside before the for loop. Otherwise, everything is exactly the same, and the results are really strikingly different. Okay, so I am now going to switch to Python. I'll just show you the very small change in code, and then I will discuss why you see such a difference between exercise 5 and exercise 6. So here in exercise 6, in fact, I'm even excluding a lot of variables that I have initialized in exercise 5, like m and n, the number of repetitions, initializing the correlation matrix, and so on. But I do need to reinitialize this all data matrix because we are coming up with new variables here, or new data for the same variables. Now, in the previous exercise, we created this data OG variable outside the for loop before we started the for loop. Here, this is the only change. I have this data OG. I don't give it a separate variable name here, but this was data OG, and now I'm adding some random noise onto this variable here. And then, then otherwise, this is the same. The plotting code is the same. This correlation of the average is the same. So again, here we are computing the correlation coefficient matrix of the repetition unique data, and then averaging all the repetitions together, and then computing the correlation of the average repetition. And then, here I am showing the average correlation matrix, or the correlation matrix of the data average. And the results are quite striking because now, you see this correlation of the average is still pretty good, right? This is still a pretty decent representation of this ground truth. But in exercise 5, this one was terrible. This method was terrible. It gave awful results. The average of the correlation matrices looked nothing like the ground truth. Here, it looks a lot like the ground truth. In fact, I'm not quantifying this, so this is just a qualitative interpretation. But I think you agree that this actually looks better than this does. So it looks like averaging the correlation matrices is better than averaging the data and computing one correlation matrix. Now, why is this the case? Why do we see such a divergence between the results of exercise 5 and the results of exercise 6? What do you make of this? What can you learn from this? And how do you deal with averaging in your own data? So basically what was happening is that in the previous exercise, so in exercise 5, the trial unique or repetition unique noise was so much more powerful. It was so much has such larger amplitude compared to the original signal that the single repetition correlations were dominated by the noise, and so therefore it was better to average over the signals. But in this exercise, in exercise 6, the amount of single trial noise was smaller. There was less single repetition noise, so therefore the single repetition correlation was more dominated by the true underlying structure, which is this variable covars. Now, what does that mean for real data? It's really hard to say. This is something that you have to evaluate on a case-by-case basis. So it will happen that in some data sets, there are certain features or characteristics of the data set or different ways that the data were collected, different calibrations of the sensors or the measurement devices, where averaging the data first is the right way to go. And there will be other situations where averaging or computing correlations within each repetition first, and then averaging the correlation matrix is the right way to go. I cannot give you a specific guideline for when to use which approach and whether to average the data or average the statistical descriptive characteristics that you extract from the data. That's something that you have to become an expert on in your domain, and you have to make informed decisions about when to average in different ways. Welcome to exercise 7 of chapter 12. The purpose of this exercise is to explore the impact of the Fisher-Z transform on the statistical significance of a set of correlation coefficients. Okay, so here's what you want to do. You want to create, let's start with describing one data set. So describe one data set as a pair of variables with a sample size of 30 and impose a population correlation of 0.1. So normally distributed random numbers, two variables of random numbers, n equals 30 for each variable, and then impose a population correlation of 0.1 using this equation. I'll scroll up to this equation in a moment. Okay, so that's one data set, and then you want to repeat that 22 more times, so you get 23 data sets in total. Now, these are all random numbers drawn from a population with a correlation of 0.1. But the question is, in our sample of 23 empirical correlations, do you get a statistically significant difference from a average correlation of 0? So basically, you take these 23 correlation coefficient values, put them into a t-test, and test against the null hypothesis of 0. So you run that t-test twice, once just on the raw correlation values, and again on the Fisher-Z transformed values. And then you can print out the results like this. In this case, we can see that the t values for the raw coefficients and the Fisher-Z coefficients were not the same. Not surprisingly, Fisher-Z transform warps the correlation values, but they were pretty similar. And here I've also printed out the critical t value corresponding to 0.05. So this means that in both of these cases, the conclusion that we draw from the data is the same, regardless of whether we applied this transformation. So that is the first part of this exercise. There's another part that involves taking this code that you write here and embedding it in a for loop over a range of correlation values. I'm going to talk about that in a moment. First, I want to show you the equation, and then I will show you the code to implement this first part of the exercise. So here is the formula to create two random variables, x and y, that have a correlation coefficient or that are drawn from a population with a theoretical correlation coefficient set to r. So normally distributed numbers, a standard normal distribution of random numbers, and then you just apply this formula, and then variable x and y will correlate with each other at the expected value of r. Of course, in finite samples, especially small samples, you're not guaranteed to get exactly r, and that's why we are doing this t-test here. Okay, so now I will show you the code for this first part of the exercise. So here I specify the sample size and also the number of samples. Here is a for loop and pretty straightforward. So this is the direct implementation of that formula that I just showed, equation 22. And then here I take the correlation coefficient between them. Okay, so then I do a one sample t-test on those correlation values to see if they're different from 0. And here I apply the inverse hyperbolic tangent, which is how the Fisher-Z transform is applied on those same correlation values. Okay, and then I print out the t-values. And yeah, here's the critical t-test. Okay, so in this case, both non-significant. This is the critical t-value. These are the observed t-values, the empirical t-values. They're not the same, but the conclusion that we draw from the data is the same, regardless of whether we apply this transformation or not. Okay, so that's just a couple of runs, and now I'll switch back to the book and show you the next part of this exercise. So now what you want to do is take the code that you just wrote for the first part of this exercise and embed that inside a for loop to basically repeat the experiment for a range of correlation values between 0 or 0.01 and 0.5. So basically, you're just going to manipulate the population correlation value. This panel here, this plot, is basically just showing that the empirical sample correlations are a pretty good match to the theoretical correlation, which basically just confirms, number one, that formula is correct, and number two, that your code is accurate. So, and again, as I mentioned, you're never going to get a perfect match as long as you have a finite sample, especially a relatively small sample like n equals 30. Okay, so then here is the interesting plot. Here we see the two t-values. So the t-value from the raw correlation and from the Fisher-Z transform correlation coefficients. And this is the actual t-value. So I'll have a few remarks about this. I will make a few observations when I show you the code. So there's not much to this code that is different from what I showed in the previous, the first part of this exercise. So this code should all look familiar, and then I've basically just embedded it inside this vector for R's, the correlation coefficients. You can see that ranges from 0.01 to 0.5 in 21 steps. So basically, I'm storing the resulting t-values now not just in a vector, but in a matrix, because we have the raw correlations and the Fisher-Z correlations separately for each population correlation value. And then the t-statistic is also going to be the same. In fact, this doesn't really need to be inside the for loop. You can see this is independent of the strength of the correlation, which should be the case, right? The statistical value for labeling a finding as being statistically significant should be independent of the population correlation. So whatever's happening in the real world, that doesn't change the critical statistics. Okay, so let's see. Then we make this plot. And yeah, so what's interesting is that the larger the correlation value, the larger R is, the theoretical R, the more separation, the more difference there is between the raw correlation and the transformed Fisher-Z correlation. When the correlation values are smaller, closer to 0, then you see very little, if any, difference between these, at least, at this level of visual granularity. As you saw in the first part of this exercise, they do differ somewhat, but the differences get bigger, basically as you get closer to 1. And that should be not at all surprising based on what you know about the Fisher-Z transform, because it has the biggest warping effect on larger values closer to -1 and +1, right? Because the goal of applying the Fisher-Z transform is to transform a uniform distribution into a normal distribution. Okay, but another interesting thing I would like to point out here is that in every single one of these cases, we came to the same conclusion about the statistical significance. So our decision of the statistical significance was the same, regardless of whether we did a t-test across the raw correlation values or the Fisher-Z correlation values. So I think the take-home message from this exercise is that it is good to apply the Fisher-Z transform because it's kind of the right thing to do, because it helps make the correlation coefficients more amenable, more appropriate for a parametric test like a t-test. But that said, it doesn't make a huge difference in most cases because by the time it really has an effect, at the level where it's really changing the values, you're well above the statistical significance threshold. Now, interesting also to remark that this conclusion and this pattern is also based on the sample size. So I encourage you to go back and rerun this exercise, this experiment, by changing the sample size. You can make the sample size smaller or make the sample size larger, and you can see whether this has an effect, and you would come to a different conclusion about what you've learned in this exercise. Welcome to exercise 8 of chapter 12. Here we will explore cosine similarity. So the purpose of this exercise will be to implement cosine similarity based on the formula, which I'll show in a moment, and then confirm that your answer is the same as the answer that you get from the cosine similarity, which is actually cosine distance, function that's built into SciPy. And then in the next exercise, we will compare cosine similarity against the Pearson correlation coefficient. So in particular, in this exercise, create a pair of correlated variables using a sample size of 40. You can create the pair of correlated variables any way you want. You can do it in a simple way, in a more complicated way, with a correlation coefficient that you specify. Totally fine, up to you. Then find the cosine distance function that comes with SciPy and confirm that you get the same answer. Okay, now first I will show you these equations, 27 and 33, and then I'll switch to code. Here is one formula for cosine similarity. It is the sum of the element-wise multiplications between the two variables divided by x squared, the sum of all the squared elements, and then the square root and the product of that between the two vectors. Okay, so that's one way to express cosine similarity. Now I'll show you the other formula, which is here, equation 33. So this is the dot product between variable x and y divided by the norm of x times the norm of y. Okay, just exactly the same formula, exactly the same math. This is just the linear algebra expression, and above is a more kind of standard algebra interpretation. So here we are in the code. I chose to impose the correlation between these two variables in a very simple way. I just create x to be random data, and I set y to be x plus more random noise. And then here I compute cosine similarity. So this is the numerator, the sum of the element-wise multiplications. Here's the denominator. That's the product of the square root of the sum of squared elements between x and y. And then cosine similarity, I call this me. This is my implementation, is very straightforward. Okay, so now in SciPy, there's a function in the library that's called scipy.spatial. So scipy.spatial.distance. And in this distance module is a function called cosine. Now, this is actually cosine distance, whereas here we are computing cosine similarity. So you actually have to compute cosine similarity as 1 minus the cosine distance. So if you were struggling with this exercise because you were getting different results that look like this, look like complementary results, then the answer is that here we are computing cosine similarity and SciPy is implementing or returning cosine distance, which is literally just the inverse of the similarity. So there you go. That is exercise 8. And now in the next exercise, we will directly compare cosine similarity to the Pearson correlation coefficient. Now for exercise 9 of chapter 12. The goal here is to directly compare cosine similarity and Pearson correlation coefficient on the same data. So what you want to do is create a bunch of different data sets that are drawn from a theoretical population correlation that varies between -1 and +1. So that is basically the x-axis here. I call this the requested correlation. This is like the theoretical population correlation. And then you draw random samples from this population that have, these different correlation coefficients ranging from -1 up to +1. You can choose the sample size and so on. And the number of steps, I used 100 steps between -1 and +1. Here's the important thing. You want to take one of those variables and have it, give it a mean offset of 10. So that means whatever are the numbers, the numerical values in one variable, the other variable, which you impose the correlation on, then just add 10 or subtract 10. So somehow set the mean offset to be 10 between the two variables. And then you want to compute the Pearson correlation coefficient and the cosine similarity. And then you plot both of those here. So panel A shows the sample correlation and the sample cosine similarity as a function of the theoretical population correlation. And here in panel B, we have one by the other. So the empirical sample correlation by the sample cosine similarity. Okay, so I'll have a few remarks to say about this, but I'll do that after I show you the code. So here are the correlations that I will impose on the data. I use a sample size of 500. Of course, you can use whatever sample size you like. And in fact, I think it's interesting to change this sample size and see if that has an effect on the results that we will produce. Okay, so here is the for loop over the range of correlations, theoretical population correlations. This you've seen before, just imposing a correlation between two variables. Here is the mean. I call this the mean decentering. So I'm just imposing an offset of 10 on variable x. Okay, and then I compute the correlation coefficient and the cosine similarity. Now, you saw, or you implemented in the previous exercise, cosine similarity manually by implementing the formula directly. In practice, you can do that if you like, but it's easier just to use the spatial.distance, scipy.spatial.distance.cosine function, and just make sure that you're computing 1 minus the distance if you want cosine similarity. Okay, so then we can make this plot. Now, I have a longer discussion in the textbook about why these two differ and how to interpret that difference and when you should use correlation, when you should use cosine similarity. But the upshot here is that the mean offset has a big impact on cosine similarity because the formula for cosine similarity does not involve any mean centering. So I showed the equations in the previous video. We can scroll up to the code from the previous exercise. You can see that nowhere in this code to compute cosine similarity do we demean. We don't mean center the data. So any mean offsets are going to impact the cosine similarity, but they will not have any impact on the correlation coefficient. So it's interesting to comment out this line and run this again. And now you can see without mean centering, the results, so the cosine similarity and correlation, Pearson correlation, are really, really close. If you zoom in, you'd find they're actually not identical. And the reason that they're not identical is that these variables they're drawn from a population with a mean of 0, but the sample mean is not going to be 0 just because of, random number selection. But the mean will be pretty small. Okay, so let's see. And now we can do, something in the middle. I demean, or I impose a mean offset of 3 instead of 10. And now you see that the lines are less convergent than when I left the data with an expected mean offset of 0, but not as extreme as with 10. Okay, and then you see here they are quite concordant, but actually I want to go back to how it was originally. Okay, so mean offset of 10, and then you see, so these data points here are fine, and these data points here are fine. Basically, it's comforting. It's not surprising to see that there's a concordance in at least the sign, if not the magnitude, between the correlation and the cosine similarity. So, the magnitude is different, but the signs are the same. So if you're analyzing these data, you would come to the same conclusion. These two variables go up and down together, or one goes up while the other goes down, based on, in all of these cases. But then you have these cases here, these disconcordances, these inconsistencies, where the correlation is negative, but the cosine similarity is positive. So that is something I find troubling because that means that literally your conclusion about the direction of the effect will be different depending on whether you use Pearson correlation or cosine similarity. So I don't know what to say about this. It's just this happens when you have mean offsets. And partly that's because of sampling variability. You can see is more likely to happen when the correlations are relatively modest. So when the effect is smaller, you're more likely to get these disconcordances. And yeah, I also encourage you to explore qualitatively, or maybe you can do this rigorously in an experiment if you like, but just play around with the sample size, make the sample size smaller or much larger, and see if these two measures appear to be more consistent with each other when the sample size is larger, for example. Now for exercise 10 in chapter 12. The goal of this exercise and also the next exercise is to produce a correlation matrix in a real data set that we will download from the web and do a little bit of very light processing, importing in Pandas and some visualizations in Seaborn. So if you are comfortable with the statistics concepts, or actually, let me rephrase that. The statistics concepts in this and the next exercise are super simple. Nothing complicated, just creating a correlation matrix from a pandas data frame. But what makes this exercise a little bit tricky is just working with pandas and working with Seaborn. So if you are struggling with the code for this exercise, then it's totally fine. Just check out the solution file I have online or watch the video. It's just most of this and the next exercise is just gaining more experience working with pandas. Okay, so anyway, your task is simple. Import a dataset and compute a correlation matrix. Okay, so it's this dataset. It's the auto MPG dataset. Here's the URL. If you want to work with this completely on your own, then that's great. Here's the URL. You can also get the URL from the online code, and then, just like don't copy or look at the rest of my code. You will need to go to this website and read a bit about the data set and the data organization, because not all of the data, for example, the column headers are not included in the data file. So you'll need to add those yourself. Okay, now you can see that, so yeah, there's about 400 observations or rows of data. Columns correspond to different features. And you'll notice that these different features are mostly numeric, but there are also some non-numeric columns like car name, for example. So we cannot compute a correlation with this variable that doesn't make any sense. So what you want to do is import the data. You might have to inspect the data and see if there's any problems or missing data values that you need to address somehow. And then you want to basically ignore any of the non-numeric columns. You can exclude them. You can just save them for excluding later from the correlation matrix, as you like. Okay, and then after you import the data, you want to create histograms of each feature to produce a figure that looks something like this. So here we see the histograms of miles per gallon, number of cylinders, and so on. And then what you want to do is create a correlation matrix that looks like this. Now, I used a Spearman correlation here because the data are of mixed type. Some of these data, so these are all numerical data, but some of these variables are ordinal, some of them are ratios, some of them are interval. And you can also see that the distributions are non-normal. This one looks beautiful. This is a really normal looking distribution. This one looks kind of normalish. It's a bit skewed. But this is clearly non-normal, clearly non-normal. So rather than having to worry about each of these variables and thinking about applying various transformations to these variables, instead I decided, you know what, it's better just to go with Spearman correlation and don't worry about meeting the assumptions of of Pearson correlation. So that's how I got to this correlation matrix here. So you can see this is a matrix where the element at each the numerical value at each element in this matrix is the correlation between each pair of variables. So the correlation between the number of cylinders and the miles per gallon is minus 0.82. That's not that surprising that you get such a strong negative correlation, right? The more cylinders a car has, the less miles per gallon it's going to get. Obviously, the diagonal is trivially 1. And yeah, so, as I mentioned in the beginning of this video, most of the work in this exercise is just figuring out how to work with pandas and seaborn to produce a figure that looks like this. So here we have the URL for the data, and we can just import that directly here using the pandas function read CSV. Now, the column names are listed in the website here, but they are not directly embedded in the in this data file. So therefore, I also include the column names here that I have basically just copied from the website. Now, it turns out that there's some missing values in this data frame, and those are in the data set, in the data file, they are listed as question marks. So here I specify that the NA values, the missing data values, not a number, values are indicated in the original data as a question mark. Okay, so we can import this and just have a look through this data frame, and you see this is what it looks like. So you should get something that looks like this. Okay, so then here I'm going to drop the non-numeric columns in the data. Now this origin one is a little tricky because it looks like it's numbers, but actually when you read about this data frame online, you will see that this origin actually corresponds to a geographical location. So it's not the case that 2 is twice the value of 1. These are not actual numbers. These are just codes for a geographical location. Okay, so there's a number of ways you can do this. I chose to just create a new data frame, a new Python variable that excludes or drops these 2 columns. So now I'm going to be working with this data frame data underscore numerical. Okay, yeah, so then in a bunch of different subplots, I'm just going to use Seaborn to create a histogram of these data for each individual column in data numerical columns. Okay, so yeah, so that's it. And then here, this is just turning off the axis here because there's nothing here, so I just leave it as white space. Very nice. So this is a visualization of the distribution of the numerical variables in the data set. And as I mentioned a moment ago, I looked at this and decided to use a Spearman correlation based on the various distributions that we have here, non-normal distributions and somewhat limited distributions here. In fact, here it could also be appropriate to do a Kendall, although this is, yeah, it's the only one with such a restricted distribution. So I think Spearman is also fine for that case. Okay, so here, now we can compute a correlation matrix. I call this R. This actually turns out to be another data frame. This is not like a NumPy array. This is another data frame, and we obtain it very simply by using the core method on this variable, this data frame here. And here I specified method equals Spearman. If you leave this blank, the default is to compute a Pearson correlation. Okay, so then, yeah, I just add the annotations, which is just going to get the numerical value for this heat map from each individual element and plot that on top. So here we go. This is our Spearman correlation matrix. If you like, you can create another figure using Pearson and see if you get any real differences here. I suspect that there won't be any. Of course, the exact numbers will be different, but I would be surprised if there's any real substantial differences between Pearson and Spearman in this case, because most of these variables have at least a kind of normal-ish looking distribution, at least, normal enough, like with one peak and going down on both sides. That's usually sufficient, and there's no outliers here. That's usually sufficient for Pearson and Spearman to give qualitatively really, really similar results. The final thing I want to mention here is that this is purely qualitative. We are only qualitatively inspecting these correlation coefficients. And the reason why I say that this is limited to qualitative analysis and interpretation is that we have not performed any inferential statistics. So there's no p-values, there's no t-values, there's no significance thresholding. So therefore, we cannot say which of these are statistically significant. We don't know which of these correlations we can interpret. Now, it's pretty obvious that a correlation of 0.95 is going to be statistically significant with a sample size of 400. But, there's other, 0.3. It's not so obvious, 0.28. It's not obvious that this necessarily is going to be a statistically significant correlation. So in order to interpret these correlation coefficients, we need to perform inferential statistics, get p-values and so on. And that is the goal of the next exercise. This exercise follows up from the previous exercise, so you definitely need to have gone through exercise 10 before working through this exercise. Now, the goal here is fairly simple, but the implementation can get tricky. So the goal here is to reproduce the correlation matrix which you already produced from the previous exercise, but with a couple of additions. First of all, you can see that the diagonal elements contain no number. There's no number in the diagonal elements, and that's because the correlation on the diagonals of the correlation matrix are trivially equal to 1, right? Miles per gallon is correlated perfectly with miles per gallon. So there's no point in displaying any number on the diagonal. So you want to remove those numbers. You can see that the correlations are also here. And then there's an asterisk afterwards. And the asterisk is for statistical significance. So any number, any correlation coefficient with an asterisk next to it is statistically significant at p less than 0.05, corrected for multiple comparisons. And here I use the Bonferroni correction method. Now, when you're implementing Bonferroni correction here, you have to remember that Bonferroni is based on the number of tests. It's different from like FDR correction, for example, which is based on the distribution of p-values, the shape of the distribution. Bonferroni is purely related to the number of tests. So how many tests are there in this correlation matrix? It is not equal to the number of elements in this matrix. And that's because this correlation and this correlation are exactly the same. This correlation and this correlation are exactly the same. So basically this matrix is symmetric. And furthermore, we do not need to test the diagonal elements because, yeah, as I mentioned, they're trivially 1. So Bonferroni correction, you actually have to figure out how many unique correlations are there in this matrix. So it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and so on. But what I would like you to do is figure out or look up online a formula to determine the number of unique elements in a correlation matrix. It's the number of elements above the diagonal, basically, or below the diagonal, excluding the diagonal, of course. Okay, so that is part of this exercise as well, figuring out how to get the Bonferroni correction. And then, yeah, you're also going to have to worry about NANs. You're going to have to deal with getting not only correlation coefficients, but also p-values using scipy.stats.spearman_r. And yeah, I mean, basically, as with the previous exercise, there's quite a bit of finagling and figuring things out in Pandas and in Seaborn in this exercise. So if you're struggling with the libraries, then don't worry about it. It's totally fine. Just check out my code, and then you have that code to use for the future. I mentioned earlier in the chapter, and also you discovered in a previous exercise in this chapter, that the scipy.stats correlation functions, including Spearman and Pearson, compute correlation coefficients and also p-values, but they do not accept NumPy arrays or matrices as input. So that is a little bit annoying, but not super problematic. But it turns out that they actually do accept matrix input if that matrix is in a pandas variable. So if you have a pandas data frame, then you actually can just input that data frame and get a matrix of correlation coefficients and their corresponding p-values. And so that's what I do here. So we input this data.numerical data frame. This is a variable that we created in the previous exercise. And now it turns out that there are NANs here. There's missing data values, which were initially encoded in the data file as question marks. And here then I changed them to NANs. So here we have to say NAN policy equals omit. This means that the Spearman R function knows to ignore any data observations where there is a NAN value. Okay, and I'll show you in a moment. I'll come back to this and delete this optional input and show you what happens. Okay, so then something else that's a little bit just kind of tedious and just something you have to learn how to deal with pandas. These outputs here are actually not data frames. They are data series, which is a slightly different variable type. It's almost the same thing. Some aspects of a data frame and a data series are the same, but they're not identical. But it turns out that to get these matrices to work with the heat map here, down here with Seaborn, these need to be data frames. So here I convert these into data frames. So that's the correlation matrix in a data frame format and the p-values matrix in a data frame format. Okay, so here we have the Bonferroni threshold. It's 0.05 divided by the number of comparisons. And the number of comparisons is the number of unique elements in a correlation matrix, ignoring the trivial diagonal elements. And it turns out that there's a formula for that, which is m times m minus 1 divided by 2. So m variables or m features in the data frame. And, you can imagine that if you just want to know the total number of elements in a matrix, if it's a square matrix, it's m by m, the total number of elements is m squared, of course. But we don't care about the diagonal, so then it's not m squared, but m times m minus 1. And then we just want half of those because they are symmetric across the diagonal. So that's the intuition behind this formula. Okay, so then I create a new data frame here called significant, and that's just a Boolean. It's wherever the p-values are less than the Bonferroni corrected threshold. Okay, so then I have this double for loop, so I'm looping over all of the elements in the matrix, and I'm basically just redefining this matrix here, which is string. So I just convert the numerical values of the correlation coefficient into strings. And then, so if they are non-significant, then I'm just printing out the correlation value itself. If they're significant, I print out the correlation and then an asterisk. And if I equals j, which means we're working on the diagonal, then I don't print out anything, just an empty string here. Okay, so a lot of finagling to do. Also took me more than 30 seconds. I won't say how many seconds, but certainly more than 30 seconds to figure out all of this code because I personally don't find pandas to be super intuitive. I don't actually like it that much. But anyway, so once you get all of this finagling and housekeeping stuff to work, then displaying the correlation matrix as a heat map is pretty simple using the annotation array that I built up here as the annotation text. Okay, so then you get this. Now, it turns out that all of the correlations in this data set are statistically significant. So 0.27 is more than strong enough to be significant at 0.05 when correcting for all of these multiple comparisons using the Bonferroni correction method. Okay, the last thing I wanted to show you here is what happens if you don't specify a policy for how to deal with NANs. Basically, you get some empty cells in here. And here, this is because horsepower, this variable horsepower, has some missing values in there. And so they get coded as NAN and they get dropped from here. So if you're ever displaying a correlation matrix using Seaborn, and you see something like this, you see a column and a row that is empty, then you know that there is at least one NAN. There's some missing values in here that you need to go back and deal with.